Hello students, in this video I would like to explain parity generator, parity checker and VHDL code for it, and we'll see the execution also. Before that we'll see what is a parity generating technique. Parity generating technique is one of the most widely used error detecting technique. Remember, it is error detecting code. Error detecting code that is used during the data transmission. We know that in digital systems, when binary data is transmitted and processed, the data may be subjected to noise. That means the data, when you will be sending the sequence of ones and zeros, the binary information, sometimes because of the noise, the bits can be altered. Instead of 0, it could be 1. Similarly, if you try to send 1, it receives 0. So in order to ensure that whatever data that we are sending, the same data is received by the device. In order to ensure that, we are adding this extra bit. So this extra, the parity bit is an extra bit that we are adding at any place. Here I've taken a simple example. At transmitter end, what I'm doing is, along with my data, in this example I would like to transmit a byte of information. Byte means 8 bits. So for example, if my data is D0 to D7, along with the data, along with this 8 bits, I'm adding this extra 9th bit. The 9th bit, that is called a parity bit. That is, the bit is called as parity bit. We are adding this extra bit, ensuring that at receiver end we could able to receive the data properly or not. It is error detecting code. It can able to detect 1 bit error. We'll see how it is. And at receiver end, the number of ones and the message is counted. See, it is counting number of ones. If it does not match with the transmitted one, then it will show. Then it will give you an error message. There are two types of parity bits. First one is odd parity and the other one is even parity. Odd parity and even parity. First we'll see what is an odd parity. If the number of ones in the binary code is odd, then we call it as an odd parity. Say for example, the data that I am sending is 1010, any random data. Here we have taken example of a byte. So here I am taking my data as 10101110. And you can, I hope you can able to count the data bits. Check how many ones are there. 1, 2, 3, 4, 5. The number of ones in the given binary code is odd. We call it as odd parity. And similarly, even parity. Here is the example. If number of ones in the given code is even, then we call it as even parity. Now I hope you understand what is even parity and odd parity. Now we'll see what is this parity generator does. This parity generator simply adds an extra bit called parity bit, ensuring that you're transmitting. See, parity generator is used at transmitter end, and parity checker, we verify the data at receiver end. Okay, so at transmitter end, this parity generator ensures that the data is even all the time. Say for example, if you want to transmit a byte of information, we'll take this data, this example. Say for example, if your data is 1111, a byte of information, I'm talking about a byte. So this is what is the data. If you check the number of ones, 1, 2, 3, 4. Yes, there are 4 ones. That means the data is already even. So this data, D0 to D7, this byte of information is already in even nature. So that extra bit is now going to be 0, ensuring that it is an even data. And similarly, if your data is 1111 0001, that means if you count number of ones, there are 5, 4 plus 1. So now it is an odd parity, isn't it? It is an odd parity, but we try to generate even parity. Then we ensure that this extra parity bit is equal to 1, ensuring that the data is even. Okay, I hope you understand the difference. Now it is a 3-bit parity generator. It is a 3-bit parity generator. This information you can go through. Yeah, 3-bit parity generator. This is my message. A, B, C are the inputs. A, B, C are the inputs, and this is parity bit. If you check, first data that I'm sending is 000 so if you see number of ones, they are 0. So it is already even. So the even parity generator generates it is equal to 0. If it is 001, see number of ones are odd. Number of ones are odd. So in order to make this data even, that extra 4th bit is now 1. So now the data is 0011. So it is now in even in nature. Next one 0101. It is already 010. So the number of ones are 1. So it is odd. So we made this is equal to 1. This extra parity bit. Next 3 it is even. So parity bit is equal to 0. 4 it is odd. So parity bit is equal to 1. 101 it is even. So parity bit is equal to 0. 110 even number of ones. So it is equal to 0. 111 odd. So the parity bit is equal to 1. That is how we'll design. If you check its minterms logic, for 1, 2, 4, 7, this parity bit is equal to 1. My parity bit is equal to 1 for the combinations 1, 2, 4 and 7. That is what is written over here. Okay, if you put that in the K-map, that equation that we are going to have is A XOR B XOR C. If you want to simplify the same using equation simplification method or Boolean postulates method, then you can simplify it. Finally, the answer is A XOR B XOR C. So you require 2 XOR gates in order to simplify this equation. If you want to execute a data flow model of if you want to write a data flow model of this data flow model using VHDL language, you can write this way. You can declare P as output. I hope my students does know how to write VHDL code. Yeah, so under entity I'm going to declare ABC as in bits. So in std underscore logic, I'm just explaining only the basic logic, and P is the output. P or X or Y, it's up to you. Out std underscore logic. This is how you are going to fill your entity. Next, coming to the architecture, my P is equal to A XOR B XOR C. That is how you can write the program. Under architecture, the logic is P XOR B assignment A XOR B XOR C. Here is the program. Here is the program in behavioral model. So these are the library statements. Under entity, I have declared X as my input. So instead of ABC, I have taken it as X of 2, X of 1 and X of 0. So I am declaring it as an array. So it is now X of 2 down to 0, and then Y is the output. I think I have given say over here. Let it be anything. Okay, let it be anything. So X colon in sorry, it is std underscore logic ma. Std underscore logic underscore vector, and it is out std underscore logic. Yeah. Under even parity generator, it is port X in std underscore logic. Now we have declared input as array and C is the output. Coming to the architecture, begin process of input, then begin. We have the combinations over here. The combinations are 1, 2, 4, 7. 1, 2, let me clear this. Yeah. So for the combinations 1, 2, 4, 7, we have taken it in minterms logic, isn't it? If you check, you can check that in the truth table. 1, 2, 4, 7, your output is equal to 1. So the program is also the same way. If it is array now, so X is taken in double quotes. So if X is equal to 1, 2, 4, 7, then output is equal to 1. If x is equal to 1, 2, 4, 7, then see output is equal to 1, because if you can check that the data is odd. If the data is odd, this extra parity bit is equal to 1 in order to make it as even. Okay, else it is 0. If you interchange this 1 0, you can get the program in odd parity, program for odd parity generator. Now it's an even parity generator. So this is what is the program, and here is a test bench. Now we'll see the execution. Here is my program, and this is the test bench. So here under signal declaration I have given all zeros, and then it is 1, 2, see 1, 2, 4, 7. So for first 0 it is even, then for the remaining 4 cases I have given first odd cases and then even cases. And if I simulate it, if I simulate it, my answer now is 0, 0, 0, 0, 0, 0. Input is 0, 0, 0. It is even in nature, so it is generating even bit, even parity. So in order to make it as even, my parity bit is also 0. Next combination 0, 0, 1, 0, 0, 1. It is odd in nature. See, input is odd. So in order to make it as even, my parity bit is equal to 1. Next combination is 0, 1, 0, 0, 1, 0. So it is having odd number of ones. So this parity bit is equal to 1. So now it is even parity. Next 1, 0, 0. It is odd. So the parity bit is equal to 1. Next 111. It is also odd in nature. So we made this parity bit is equal to 1. Next 3 cases it is 0, 1, 1. So it is even. So parity bit is equal to 0. Then 5, 1, 0, 1. 5 is equal to 1, 0, 1. For this combination, my output is equal to 0. Next combination 1, 1, 0. It is already even. So the parity bit is equal to 0. That is how we'll write a parity generator program. So this is the execution for parity generator. Okay. Coming to parity checker program. These are the header files. I hope you understand. Let me show you the information. So we have transmitted the 3-bit information along with the parity bit. So at receiver end you're going to receive 4 bits. Okay, using transmitter we have transmitted 3 bits. Okay, now along with parity we have transmitted 3 bits. So now there are 4 bits at receiver end, A, B, C and parity bit. Now if you receive an even parity bit, even parity data, even parity data, then we put the output is equal to 1, indicating that we have received the correct information. If you receive an odd information, then we give 0 as indication to specify that we have received an error message. I hope you understand. We have transmitted this entire data along with these 3 bits, this extra bit. So we have transmitted these 4 bits. If you check using these 4 inputs, now there are only 8 combinations. That means that there could be another 8 combinations under parity checker. So there might be a possible to have those 8 combinations, that is odd parity information. So if you are having odd parity information, you can check that over here, 0, 0, 0, 1. Okay, that never exists, isn't it? Because we have sent only even data, but now I see an odd parity data at receiver end. So it indicates that the indication shows that we have received an error message, that is indicated by 0. So 0, 0, 1, 0, it is odd, so we are making it as equal to 0. Then 0, 0, 1, 1, it is even in nature, so we give a tick mark over here, so that is indicated by 1, and so on. You can go through that. So if you write list of ones, so these are the combinations that makes output is equal to 1. And coming to the program, you can write all the list. Okay, so see, this is even 0, 0, 0, 0. It is even data. Then the next combination is 0, 1, 1, 0. Next combination is 1, 1, 0, 0. Next 1, 0, 1, 0. 1, 001. You can check the number of ones over here.